what have I solved? Just to be fussy, I plugged it into y prime prime plus y equals to 0, where y prime is what? Not dy dt, but dy dx, right? Sorry about that. I switched independent variables midstream. Didn't mean to do that. That was an accident. Now, but no, I mean, this is not a big thing on the next test. I'm encouraging you to believe in yourself that this is something you can already do. In fact, this is something you won't be required to do on a test until about mid-Math 334. Dr. Skambordis is covering it about right now. I have put this on tests before in Calculus 2, and students can do it. It's not a big deal. It really is not. You're just still learning at the moment, so it seems mysterious and like some sort of Asgardian magic or something. But okay. Now, so let's go back to the main task at hand, which is how do you solve first-order differential equations, right? So the answer is not usually with power series, all right? Not usually with power series. How to solve my first example. How do we solve dy dx equals to x squared y squared? By the way, power series would be the wrong tool here because of the y squared. This is a nonlinear problem. Power series is really only a good tool. It's a better tool for linear problems. For nonlinear problems, it gives me pause. So this one here, we can solve by what's known as separation of variables. Separation of variables. All right, so this gives me dy over y squared equals to x squared dx. And then what do? I mean, integrate both sides is the answer. So if you can separate the terms with x and the terms with y, then the problem is said to be separable. This is. Now we integrate. What do we got? We got minus 1 over y equals to 1/3 x cubed plus a constant. This is, by the way, a first-order differential equation. How many constants do we expect in the answer? Just one, right? My previous and scary, confusing example had 2 because it was a second-order problem. Sorry, I have, what have I done in the last example? I've combined 2 scary new things to make an even scarier example, right? So the one scary new thing is a power series. The other scary new thing is a differential equation. I put them together to make the ultimate evil. So my apologies. Anyway, and then so this already is what's known as an implicit. This is an implicit solution. What does it mean, implicit? What's that terminology? Implicit means that y and x are somehow intertwined by some relation, but not necessarily of the explicit form. What's an explicit solution? Solve for y equals stuff is explicit solution. What's an explicit solution? Can you find an explicit solution in this case? I mean, I would suggest that we put the minus to the other side, right? and take the reciprocal of both sides, what do I get? I get minus, I mean, I can say I get minus y is 1 over 1/3 x cubed plus a constant, yeah? So therefore, y is minus 1 over, 1/3 x cubed plus a constant. There you go. That is the explicit solution, the explicit general solution to the first differential equation that I showed you. Let's do another. dy dx equals to minus x over y. Can we find the general implicit solution to this problem? Is it separable? We've got y dy equals to minus x dx, right? Integrate both sides. And we get what? 1/2 y squared equals to minus 1/2 x squared plus some constant. I recommend that we rewrite our general solution. I mean, already that's you could say, okay, great, I'm done. Implicit general solution, hooray, done. But I think we can do better here because I'd like for us to recognize what we're looking at. I can rewrite this as x squared plus y squared equals to 2c. Can you think of a better name for 2c? If I'm looking for the solution set x comma y such that x squared plus y squared equals to 2c, can c be negative? C cannot be negative. If c was negative, there's no solutions, right? So without loss of generality, if we're trying to understand the solution set to this equation, I might as well write 2c as r squared, right? Because if I do that, then I can graph solutions to this problem. They're what? Circles, yeah. So the solution set to this differential equation are concentric circles centered at the origin. To get from one solution to another, do you just add a constant? I know, the solutions are related in a way that's more interesting than the way antiderivatives are related, right? If I wanted to find an explicit solution, say I wanted to find like this one, up here, I could solve for something like that. That would be something like y is equal to the square root of r squared minus x squared. That would be something like that kind of solution. There are two different kinds of explicit solutions, right? Upper halves, if you like, of the circle, or if you wanted to find the explicit solution down here, that would be what? Minus the square root of r squared minus x squared, right? But the implicit solution contains both cases at once, right? Because a level curve has much more flexibility in the kind of curves it can describe than a graph, right? A graph has to pass vertical line test, but an equation doesn't have to do that, right? The solution set to an equation is much more interesting. What's geometrically possible? What do these look like? What's the solution set to this differential equation look like? I don't know. Honestly, I don't know. I don't want to picture it. All right? So what I'll do next, all right, is talk more about where first-order differential equations can come up. One interesting way they can come up is if you're trying to find the so-called integral curve to a vector field. Do you guys know what a vector field is? You know, something like arrows that go along some direction, you know? Like a vector field is like telling you a field of arrows. Integral curves to the vector field are just curves that kind of like line up. They're flow lines, if you will. That would be like an integral curve to that vector field. So I'll describe next time how a first-order differential equation naturally comes up if we're looking for integral curves to time-invariant vector fields. And I'll describe more of this technique. There's one other technique. We only really learned two techniques in here. The one is separation of variables. The other is the integrating factor method. And that's it for differential equations here, plus some just basic applications. So, thanks, guys. See you tomorrow.